In this video, we'll continue to look at motion. We'll look briefly at speed, velocity, speed time graphs, velocity time graphs. We will analyze these graphs and we'll show how we can determine distance traveled, displacement, and acceleration from these graphs. So let's talk about speed. Now, we would have met speed in previous videos, so there's no need to spend a lot of time on speed. So we'll briefly define speed, state its units and the symbols, and how to calculate speed. All right? So let's talk about speed. So when the term speed is mentioned, then what basically comes to mind is how fast something is moving, right? But of course, the definition of speed is more scientific. So we say that speed is the rate of change of distance, right? So speed is a rate of change of distance. Now, as mentioned before, in some books you may see speed being defined as the rate of change of distance with time, but usually when you see the expression rate of change, that usually implies with respect to time, and therefore in some books you may see with time being omitted, right? So speed is a rate of change of distance. The symbol for speed is V, and of course the SI unit of speed is the meter per second. And of course, based on the formula for calculating speed, of course we'll see why the unit of course is a meter per second. Now, to calculate speed, in particular average speed, is equal to the distance traveled over time taken, right? So the average speed is found by dividing the distance traveled by a body by the time taken, and using the symbols we see that V is equal to S over T. Alright, now as mentioned, we'd have met speed before, and we can actually relate this formula to distance time graph we looked at previously. And of course, if you recall, if you have a distance time graph, then you can actually obtain a body speed by finding the gradient of a particular section of the graph. So the gradient of a distance time graph gives the body's speed, right? And you see that average speed is equal to distance traveled over time taken. Now we said before that the SI unit of speed is the meter per second, right? So let's talk about uniform speed or constant speed. Right? Now, previously we met situations in which a body would have been moving and it moves a certain distance in a certain time, and we're able to calculate average speed. Now, in a previous example, we spoke about, for instance, an athlete who completed exactly one lap of a 400-meter track and in a time of 50 seconds, right? Now, the average speed for that particular athlete was obtained by dividing the distance traveled over the time taken. So the distance traveled, of course, was 400 meters rather, and the time taken was 50 seconds, and that gave us an average speed of 8 meters per second, right? Now, the average speed being 8 meters per second, does this mean that the athlete was moving at this speed throughout the entire race? No. There were some times, at some points in the race, athlete was going faster, and at some other points it was going slower. So its average speed for the entire journey, 8 meters per second, right? Now, when we speak about uniform or constant speed, as the word implies or the expression implies, it means that speed which is not changing, right? So when we speak about uniform or constant speed, we're talking about a body which is basically covering equal distances in a given time period, right? So a body speed is said to be constant So a body speed is said to be constant if it covers equal distances in a given time period. Right? Now, what exactly does this mean? Suppose we're told that a body is moving with a constant speed of 10 meters per second, right? So a constant speed of 10 meters per second. What exactly does this mean? This basically means that this body will be traveling 10 meters every second. So for every second that elapses, its distance increases by 10 meters. And that is what we mean by a constant speed of 10 meters per second, right? Now, having said that, let's look at speed time graphs. Now, in previous videos, we would have looked at distance time graphs and displacement time graphs. And a distance time graph is essentially a graph which shows our body's distance traveled changes with time or varies with time. Similarly, a displacement time graph shows our body's displacement varies with time. So similarly, a speed time graph is a graph which shows how our body's speed. So it's a graph showing the variation of a body's speed with time, right? And as expected, based on the speed time, speed goes on the y-axis. So speed on the y-axis is plotted against time on the x-axis, right? Now, typically, the SI units of speed and time are used when drawing these graphs, but of course, it is not uncommon to see speeds given in kilometers per hour, miles per hour, and the time in hours, for instance, right? So, whereas the SI unit of distance is a meter, and that of time is the second, it is not uncommon to see different units being used, especially with these graphs, right? So we'll look at a basic speed time graph and we'll analyze the graph and we'll talk about how the body speed is changing and if it is accelerating or the point at which the body is accelerating and so on. So let's look at a simple speed time graph. So this is a speed v in meters per second against time in seconds, right? So a simple graph slopes up like that, remains that's horizontal. So let's give it a little bit more space. Right? Let's call this point O, this point A, B, C. Right? So, shape of the speed time graph OABC. Now let's analyze the graph. Now at O, the speed is 0 and therefore the body is at rest. So at O, the body is at rest. Now let's examine OA. Now OA is a straight sloping line, right? Now OA is a straight sloping line, which of course means that the gradient is uniform. So the gradient is uniform. Right? And what does this mean? It therefore means that the acceleration is uniform. Right? So basically, we see that, I could put it here, the gradient of the graph gives acceleration. Right? So the gradient of the speed time graph gives about its acceleration. Now, so OA basically shows a region of the body's motion in which it is accelerating uniformly from rest. So the body accelerates uniformly from rest to some velocity at A in some time. Now let's just put some values on this graph. So let this say be 5 seconds, and let this period here be 15, and let's for this value, let's make it 22, right? And let's say 30 meters per second, right? So just to put some numbers, so basically, this body accelerates uniformly from rest at O to a velocity of 30 meters per second at A in a time of 5 seconds, right? Now let's talk about AB. Now AB is horizontal. So AB is a horizontal line, which means the gradient is 0. So the gradient is equal to 0, which therefore means that the acceleration A is equal to 0. And from this, we can see that the speed is constant. So the region AB shows the body moving at a constant speed of 30 meters per second. Now it does this between 5 and 15 seconds, and so it does that for a period of 10 seconds, right? So the region AB shows the body moving at a constant speed of 30 meters per second for a time of 10 seconds. Now lastly, BC. BC is a straight sloping line, but this time, unlike OA, which is showing a positive gradient, BC is showing negative gradient. All right? So BC, the gradient is uniform and negative. Right? So the gradient is uniform and negative, and since gradient represents the acceleration, then the acceleration is uniform and negative, right? So the acceleration, so let's call that A. Acceleration A is uniform and negative. Now when it comes to acceleration, if the acceleration is negative, we typically refer to it as a deceleration, right? Now acceleration is actually a vector quantity, which means that it can be positive or negative depending on direction, right? Now we're talking about a speed time graph, so therefore direction does not come into play. So because the speed is decreasing, then that means the acceleration is negative, and this is said to be a deceleration. So for BC, we say that the body decelerates uniformly to rest. Right? So BC, the gradient is uniform and negative, which means the acceleration is negative, and therefore the body decelerates uniformly to rest. So the body comes to rest at C 22 seconds after it would have started its motion at O. Now, since we included numbers, how about the area under the graph? What does the area under the graph give us? For a speed time graph, the area below the graph gives us the distance traveled, and we'll add that here. So the area below the graph gives distance traveled. Right? And since we have numbers on this graph, we can actually go ahead and calculate the area and hence the distance traveled. Now, to calculate the area below such a graph, we can do one of two things. Since it's already broken up into three segments, this would be a triangle, a rectangle, and a triangle. We can find the areas of each and add them all up, and we get the total area, which of course gives us the total distance traveled. But of course, we should be able to recognize this shape as a trapezium, and we also should be able to find the area of the shape using the formula for the area of a trapezium, right? So if we want to go ahead and find the distance traveled, we say the distance traveled is equal to the area under the graph, right? And for simplicity, we'll just find the area of each segment and then add them all up. So this is a triangle of base 5, which would be 5 seconds, and quote unquote height 30. So the area of this piece would be base times height over 2. This gives us 5 times 30 over 2 plus this segment is a rectangle of base 10 seconds and height 30 meters per second. So this will be plus 10 times 30, and the third segment is also a triangle of base 7 seconds and height 30 meters per second. So this will be plus 7 times 30 over 2. And so we work that out, add it up, and it will give us the distance traveled for the body whose speed time graph is represented by this OABC. So 5 3 is 15 divided by 2. So this gives us 75 meters plus 300 meters plus 7 3 is 21 divided by 2. That gives us 105 meters. So when you add that all up, 75 plus 105, that is 180 plus 300, and that gives us 410